So this little video is intended to give you a few hints on solving the sort of qualitative analysis problems that we looked at in class the other day. So here's an arbitrary sort of problem, simply supported beam with three forces, and here is the likely free body diagram. So point one is that the bending moment diagram for a structure which only has point loads is made up of straight lines, and the bending moment diagram only changes under a point load. So here's the bending moment diagram for this structure. Straight line, straight line, straight line, straight line. This illustrates another point as well, which is that when a beam finishes on a pinned support, the bending moment there must be zero. Be careful though, that doesn't mean that whenever there's a pinned support the bending moment is zero. It's just when a beam ends on a pinned support. How do we draw the bending moment diagram in that case? Well, it's because we thought about the deflected shape. And we figure out the deflected shape just by imagining what must happen. So at the left hand end and the right hand end there's zero deflection. It will go up a little bit where it's being pushed up here. It'll go down in the middle. It'll go up again and it'll hit zero. So we can see that, well, a couple of things. The bending moment diagram looks a little bit like the deflected shape. It's more spiky, but it's got the same sort of shape. We can see that this is the tension side here, this is the tension side here, and this is the tension side. And we can see that the bending moment diagram is always on the tension side. And we can also see that there's a couple of key points where the bending moment diagram is zero, and they relate to the points on the deflected shape where the curvature changes in sign, or you can think of it as a point of contraflexion. I'll use a 2D shape now to illustrate a couple of other points. There's nothing inherently more scary about a 3D shape than a 2D shape. Sorry, 2D shape rather than a 1D shape. So here's a simple example. So here's a column with some sort of crossbar carrying a couple of forces. Let's look at the deflected shape to start off with. Well, there's one thing we definitely know about the deflected shape. It has to hit the ground at 90 degrees. That's what the fixed support requires. We can see that the force off to the left must pull the post slightly in that direction, and we can see the one hanging from the top must pull the post down a little bit. Now, one thing that definitely doesn't ever happen is this, where you have the force applied and then there's a discontinuity in the shape. That just doesn't happen. In fact, and you know this, the beam changes shape more smoothly than that. So it'll come over here. Now that's where the corner ends up. The corner, which was 90 degrees, must stay at 90 degrees. So as we sort of come down here, I may not have drawn that perfectly, as we come down here, that angle must stay as 90 degrees. Let's draw a free body diagram now, and then let's try and work out what the bending moment diagram is for this problem. Well, there's one thing we know about the bending moment straight away. It has a 0 value at the end here. So that's the beam finishes in midair. The bending moment there must be 0. Where it hits the ground, the bending moment won't be 0, because the bending moment that's found in the beam will be equal to the bending moment reaction at the ground. Another thing we know is that the bending moment diagram everywhere has to be straight lines and only changes when there's a point load. So I think my first observation here would be that the force at the tip of the cantilever there is tending to cause that side of the beam to be in tension. The bending moment diagram is linear, so it must carry on up from 0 like that to some value, and we don't know the value of that yet, and typically we shade that in like that. Now here's another important point, which is it's easier to show on a video than on a piece of paper. So far we figured out what the bending moment is roughly or schematically in the top beam. We're now going to look in the column. Now, since we know that what the value is in the left hand end of the top beam, we also know that it has the same value in the top of the column. Those bits of the structure are connected together, so they're always equal, and that's a feature you'll see on every bending moment diagram. Next off, I'll look at the curvature of the deflected shape here. I can see that looks like it's in tension because of the way it's curving, but as we reach this point force over here, that bit clearly is the tension side, so there must be some point where the bending moment goes through 0, because we've changed from tension on one side to tension on the other side. Now, remembering that the bending moment can only change under the point load, we've really only got two points to define. One is underneath the load halfway up the column, and the other one is at the base. So at the base, who knows exactly what the values are, but we can see that it should be plotted on that side, and under the force it must be on that side. Somewhere in between it goes through 0. Let me shade it in. The last bit is a join the dots exercise. It must be a straight line in there. We know the value at the top, and we've figured out what the sign is for the value halfway in between. So that's the bending moment diagram for that system. A quick word on UDLs, uniformly distributed loads, before we finish. So deflected shape for this system has to be 0 here and here, of course, and it'll kind of go down, sort of slightly more on this side, the other side, and then in here it straightens up, so that the bit of the beam that's beneath the unloaded part of the structure remains straight. Let's draw a free body diagram. Well, the bending moment diagram isn't terribly difficult to work out here. So 0 here and here, and curving under the UDL and straight in here because there's no forces. So it's a join the dots exercise. Some of you were wondering how we know whether it's curved in that direction, or how do we know it's not curved in that sort of direction? Well, I think the way to do this is maybe to think about making that cut. So this is the sort of thing I want you to do. So you can see the definition of M as you go distance x along the beam here, and hopefully that functional form and that definition of x persuades you of which direction the beam curves in. For the purposes of this analysis, we don't want to know exactly what the curve looks like. We're just trying to get a feeling for the overall behaviour of the structure. So it's more important to know the shape of the bending moment diagram, and most importantly, which side of the beam it's on. One final thought about using that sort of technique. So if you have a problem like this, it's a pretty daft looking structure, I think you can agree. let's draw a free body diagram. So the thing that I'm trying to point out here is that at the base, where there's the roller support, there's only a vertical force, which means that the moment in the bit of the column immediately above it must be 0, because this is the sort of thing that should go through your mind. So looking at that little free body diagram there, where x is somewhere before the applied load kicks in, m must be equal to 0. Okay, there's no other forces other than the r which acts straight along the beam, so the bending moment in there, in that part of the beam, is 0. In case you're curious, let's work out what the bending moment must be for the rest of the beam. Well, we can use the fact that we know that it can only change here and at the bottom, so the bending moment must go linearly up. Remember, whatever happens here must be the same here. That's really important, really important. Just through experience I can see that its bending moment is constant along here, and then it must go back to 0. So there we go.